Mr. McBrien. This is SCH4U, Electrochemistry 8, Galvanic cells. So the Ontario curriculum wants us to be able to draw labeled diagrams of galvanic cells and identify the components of these. And that's what we're going to go through today. So back in prehistory times, Galvani exposed a frog's leg to a current and noticed that it would twitch. And less than 100 years later, Volta figured out that this was due to current flowing through what we call electrolytes in the body. And he went further and developed the first battery based on connecting a series of electric cells together. And we now know that it's a set of spontaneous redox reactions that produce a consistent current from this battery. Okay, how do we put these things together? Well, we have the concept of cells, containers of liquid with electrolytes in it. Depending on the kind of cell, we're either going to have a source for the electricity or we're going to have a load that uses the electricity. These are connected to two electrodes that are dipped into molten or aqueous chemicals, so a liquid of some kind. And overall, this is a cell. In galvanic cells, electricity is produced, so the reaction produces electricity. In electrolytic cells that we'll talk about for a little bit later, the electricity is actually consumed. It's used to force chemicals to do a non-spontaneous redox reaction. And we'll talk about one of these in a few minutes. So let's look at this galvanic cell in a bit more detail. We also refer to it as a voltaic cell, after Volta, of course. We use a salt bridge or a porous cup, a disc, to allow ions to move to balance the charge. And we'll talk about that in a second as well. So these are two possible designs for this galvanic cell. So the salt bridge thing, remember that anytime you have a circuit, you have to have the electrons go around in a circle. Well, we have a half of this. We have the electrons moving through the wire from the anode to the cathode. But that negative charge moving from the anode to cathode, it has to be balanced. We can't build up charge anywhere in the system. So whenever we want to separate our electrolytes, whenever they're not mixed together, we use a salt bridge to let ion movement compensate for the charge associated with electrons. So this is a salt bridge here. And usually what that is a high concentration of some kind of electrolyte, and it's suspended in something to keep it from flowing. Instead, you have diffusion of the ions. So let's talk a bit more about what's going on. So we've talked about this reaction several times, the reaction of solid copper with aqueous silver nitrate. And the transfer of the electrons reduces the silver and oxidizes the copper. And this reaction is a spontaneous one. Well, we don't have any control of these electrons. We can't measure what they're doing directly. We can't observe them in any way. But if we change that reaction slightly, we can actually control the whole thing. So we can set up, instead of having one container, we can set up two cells, have a copper electrode, a silver electrode, and we can do this same reaction in a controlled manner and measure all kinds of things about it. We can measure the potential using a voltmeter. We can measure the current if we wanted to. This reaction is now working under our control. So notice what's going on. It's the same thing we discussed before. The copper is going from copper 0 to copper 2+, going out into solution. The silver is coming out of solution. The silver nitrate, silver is going from Ag+ to Ag0 and plating out onto the electrode. So this electrode is getting heavier or larger, and this one is getting smaller or lighter. And while this is happening then, these electrons, where do the electrons come from to reduce the silver? Well, they're actually flowing through this wire. And so we have a flow of negative charge across through this wire from one electrode to the other. Well, we can't build up that charge, so we have to have a flow of negative charge from here back into this solution. And this is accomplished through the salt bridge. So the negatively charged nitrate ions move through the salt bridge and out into the solution here, and positively charged sodium ions move through into the other side. So we have a balance of the charge. So again, just to be clear, negative electrons flow through to this electrode. Negative nitrate ions flow back through to balance the charge. Okay, hopefully that's clear. If it isn't, pause the movie, take a bit of time, and have a look at this diagram because it's all here. Okay, in terms of naming the electrodes, by convention we call the electrode where reduction occurs the cathode, and the electrode where oxidation occurs, we call that the anode. And here's a mnemonic for you to help you remember: red cat, anox. So oxidation at the anode, reduction at the cathode. All right, a little bit about electricity. We're not going to go into this in great depth, but it is good for us to be able to talk about some of the definitions of the things that are going on. So the driving force on that electrode, on that electron that moves through the wire, is generated by the chemistry, and we call that push, that driving force, the potential difference. And it's essentially the amount of energy that will be generated per electron. And that is a function of the electrodes and the electrolytes, and we're going to see more of that soon. Electric current, of course, is just the rate at which the reaction is going on. It's the speed, the speed of the electrons moving, the flow of charge. So the current determines how much copper is being oxidized and how much silver is being reduced per unit time, per second. And power, well, we don't really need to know about that for our purposes here. So here are some of the quantities and things associated with it. We won't spend a lot of time on these things, but coulombs is just a large number of, a large amount of charge. Amperes is charge per time. The volts are the amount of push, the amount of pressure being put on those electrons to move. Okay, so let's talk a little bit about some direct applications of the ideas. A battery then, where we started all this talking about batteries in electrochemistry, is just a group of galvanic cells connected in series. And each one of those cells gives a little extra push to those electrons, to the total battery potential. Now, secondary cells can actually be recharged by adding electricity, so they go from being a galvanic cell to being an electrolytic cell, just by virtue of pushing electricity into them. So that's what happens when we charge a battery. Here's one of those rechargeable batteries. Here's a lead storage battery like you'd find in a standard car, and that applies. Those 12-volt batteries are easily 60-year-old technology. So what we have is a series of cells based on lead. So we have lead oxide going back and forth to solid lead zero, metallic lead. And the electrolyte in this case is sulfuric acid. Now, the batteries that we use in our various devices, in a remote control or what have you, these are slightly different. So this is a dry cell battery that's based on the anode being zinc, the cathode being graphite, and the electrolyte is a paste of manganese dioxide and ammonium chloride. Fuel cells are something different. So they're interesting technology in the sense that they're a way to generate electricity based on a flow. So we might look at these as an alternative to a gasoline generator, gasoline-powered generator. So they're voltaic cells, but they're based on reactants flowing into the system continuously. So a hydrogen fuel cell then generates electricity by bringing in hydrogen and oxygen, and the only emissions associated with that are simple liquid water. So the two half reactions are given here. So hydrogen reacts with hydroxide to form water and electrons, and over at the cathode, the oxygen reacts with these electrons with water to form hydroxide. Okay, and so here's a cartoon of a hydrogen-oxygen fuel cell where hydrogen flows in, oxygen flows in, a reaction occurs in the center region, and the only emission is steam. Okay, so we have a similar problem in electrochemistry as we had with organic chemistry. And that is, how do we communicate an electrochemical cell configuration in text, briefly? So if we want to send someone an email describing an electrochemical cell that we have built, how would we do this? Well, it turns out they've designed a shorthand system for describing this very succinctly. So very briefly, we can describe our electrolytic cell or our galvanic cell just by simply specifying the material for the cathode, the electrolyte around that cathode, the material for the anode, and the electrolyte around the anode. And this double bar here represents our salt bridge. So for example, our reaction involving silver and copper that we used a few seconds ago as an illustration, well, this is it here. This is the equivalent of that picture, showing the electrolytes, both electrodes in just a few keystrokes. Now we can also do things like include concentrations for these electrolytes as well in this notation. Okay, so this was a quick review of galvanic cells and how they generate electricity using two chemical reactions. The electricity flows through a wire between the electrodes, but the charge is balanced by the movement of ions through a salt bridge or a porous disk. We have a standard cell notation that allows us to use a few characters to communicate the configuration of our electrodes and electrolytes. All right, so for your homework, please do the worksheet where you practice designing some of those notations and deciphering those notations, and please read through the notes. Thanks very much, and have a great night.